Hello to the crowd, and thanks, a lot of thanks to Carla, Andrew, and her team for organizing this. Actually, it's my first big conference since quite some time. Let me try to start this screen here and start the talk. I hope you see it. You see also from my first slide, I'm still used to kind of old style Beamer talks with big letters and not that many text on the transparencies, but maybe it's also helpful now. So let me start. This is my, I cannot switch now. Here. This is the outline of my talk. I will also talk a little bit about methods, which already Jan Michael did quite very well, so I can go quick here. But let me give some remarks on different methods. I will present a data and an experiment that is already quite some years ago, but it fits perfectly to the subject of this session here, tunneling time of an atom, a measurement and theory, and then some very new results on ionization of hydrogen, molecular hydrogen, rapid measurements where we look at sidebands and time delays. This is very fresh and still kind of under discussion from our side. Okay, so here are the methods. There are basically, Jan Michael already mentioned this, two well-established methods. One is the Attoscience clock and one is electron streaking that we heard about, and rapid. And streaking and rapid are very similar. In streaking, you use a single attosecond pulse and you streak with an IR pulse. In rapid, you use a sequence of attosecond pulses. And eventually, you get very similar equations here for the time shifts that you are aiming to measure. This is this factor A here, is tau A. And this is a sum of two contributions. It's the atomic or the pure Wigner time that we heard about. And there's an additional shift. This is coming due to the interaction of the electron with the laser in the continuum, or with the IR photons, dipole transitions in the continuum. But for both cases, this phase here is exactly is actually the same. So the method is very similar. And what you do usually, these are the famous experiments here for the neon measurements, either in streaking or with rapid, you measure shifts of traces, of electron traces for two different states that get ionized. So you have two different lines in the continuum, two different energies, and you analyze this this tiny delay here, this tiny shift in terms of delay. And here are my remarks. And from those, you already can see that I'm not that convinced about these concepts at all, but it's kind of useful to learn something, because what we all rely on is kind of a single particle or an active electron picture. Just one electron is active. We don't treat the system as a whole. And sometimes this can be very problematic. It causes kind of misunderstandings, and it also changes the values that you measure. I agree that very often you can correct for this with a good theory, but what eventually would be needed to solve this problem as a whole. It's also assumed, and this was also discussed in the last talk, that we always assume that the IR streaking field is weak. So changes of the molecular or atomic structure due to the streaking field is neglected. This is also kind of a problematic issue, because good results you get only in the limit of a vanishing streaking field. And what we measure in the experiments is time shifts or phase shifts. And from this we extract Wigner times, or in other words, shapes of binding potentials. This was also now nicely discussed by Jan Michael. So we measure the shape of a potential. And this is getting problematic if we talk about long range or Coulombic potentials. And very similar, these concepts are then, for example, to other measurements where you measure, for example, simply cross-sections of some processes. There's another method to measure times, and this is the Attoscience clock concept, also presented by Jan Michael, where we just measure a shift of the momentum distribution of the emitted electron in the plane of the polarization of the laser with a elliptically polarized light. And then we interpret this shift, this tilt in angle as a time delay. And the same holds also true here. The results and the interpretation depend on the physical model, on the mechanism. So we always rely on a mechanism. This, I agree, is the fun part because it leads to a lot of discussions. And this is what also brings us further in our understanding. But it's also a little bit kind of dangerous because at the end, I think you don't even need to use this tunneling concept in the case of a strong field. You could also describe it in terms of a multi-photon transition. So the measurement relies also on a single particle picture, one active electron. Very often we have problems or neglect even other processes, other interactions. It might work for atomic hydrogen. There will be a talk by Klaus Bartschat, I think tomorrow. And it is also sensitive to the laser parameters, also to macroscopic parameters. We do not measure time directly, we infer the time from a momentum measurement. Okay, let me come to my first kind of results, tunnel ionization of an atom. This is an experiment that we did already some years ago. And we looked for the elliptical polarized light, tunneling of an electron through the barrier. And we asked now, not about the time directly, but how good is theory? Can we understand with theory, with the model, the results that we get? We use a simple picture that we treat the tunneling process here out of through this barrier here, quantum mechanically, and afterwards the electron is treated as moving like a classical particle in the electric field of the laser, including the interaction with the remaining ion. And you know that there is a kind of a huge debate since many years, which is the fun part, I think. What is this time? Is there a time? Some experiments say there is some time. Some theories say there is a zero time. Some of them predict a time, so it depends. And why is it so difficult? Because time is not really an observable in quantum mechanics. We have no time operator, so it's hard to define even a time. And similarly, we cannot really define a starting and an end point of a trajectory in quantum mechanics. But this is needed in order to extract the time. And there are many options here to really kind of characterize or define the trajectory of a quantum particle. But this depends then also on the interpretation and the picture that we are using. So in this context, if we now discuss tunneling, we need somehow a definition of time. What do we mean with time? And we use here a very simple concept. We say, okay, we use quantum mechanics to describe the tunneling out of the barrier here. And afterwards, we use classical mechanics, a classical trajectory to describe the motion of the electron in the presence of the field and the remaining ion. So, and in order to start to launch this classical trajectory, we have to define initial parameters. And the initial parameters should be the initial momentum and the time after the maximum of the laser field at which we should start this trajectory. So once we have these parameters, the time and the initial momentum, then we can launch our classical trajectory and we should get very good agreement with experiment if everything is well described. Okay, in the experiment, we are looking to the electron momentum distribution, as I said. So if, for example, your laser electric field is polarized like here on the upper picture, elliptically elongated along the y-axis, you will measure electron momenta along the x direction. This is just because of the motion in the electric field of the laser. And you should see maxima along the px axis, and these maxima are now tilted out of the px axis, first because of Coulomb interaction of the electron with its own ion. This already leads to a kind of a tilt here, but this is just purely Coulomb interaction. There's nothing to do with the time or any tunneling time or anything else. This is one effect, a big effect. And we measure this in our lab by using a kind of a cold trans reaction microscope. So we send in a laser with circularly polarized light, long wavelengths in order to avoid some of the problems of non-adiabaticity, long wavelengths and intensities in the range of 10 to the 14, as low as possible. And we use in the experiment, and this is the trick now, a mixture of argon and krypton, two different gases. And we measure them simultaneously. So we get electron spectra for both targets in absolutely identical conditions measured at the same time. And we analyze now from this experiment just the differences between these two spectra, between argon and kryptons for different intensities of our laser. So what we do, these are the two targets with slightly different ionization potentials. Consider just one active electron. The electron is moving in a kind of a Hartree-Fock type potential that is deformed by the laser field. In the theory, then we solve the Schrödinger equation of the electron in this static field. And from this solution, then we get the initial parameters for our classical trajectories. So these are the experimental results for one specific laser intensity for argon and for krypton. And you see these spectra are again now tilted along with respect to the x-axis, and they look very similar. Actually, if you compare and have now a somewhat closer look, you see they are different. The difference is tiny. This is the difference of both spectra. It's in the order of 10 to the minus 4. So there is a small difference. And now we're going to analyze this difference. So we look to the quantities here, the ionization yield, the average radius of this momentum distribution, and the tilt angle. And for example, the total ionization yield, we plot the ratio of argon and krypton here as a function of the momentum of argon electrons, and because the momentum scales with the intensity. And if we do everything correct in our calculation, so we have to consider depletion, we have to consider focal volume averaging, the influence of the Coulomb interaction with the of the electron with the ion, all this has to go in. It's not that tricky, but then at the end of the day, you get a curve from theory, which fits very well with our experiment, if the parameters are all fixed. We can also look to the average radius of this distribution here. And we get also a very good agreement here with theory if we use a starting momentum from theory now either not equal to 0 or equal to 0 at the exit of the tunnel, if you want. And there's a slight difference here between two equations, two formulas, where one is the non-adiabaticity is included, or an effect of non-adiabaticity is such that during the tunneling, the direction of the laser field changes a little bit, and this is included in this solid line here. And again, we see a very good agreement with the experiment. And, and here is plotted the tilt angle from the distribution here. And again, the differences between the two targets. If we use the standard simple man model, just tunneling, starting a classical trajectories at the exit of the tunnel, with 0 initial momentum and with 0 time, then we get this dashed line. If we use our theory, the quantum theory, for the initial values, there is a certain start initial momentum, there is a time for kind of tunneling, if you want, then we get this solid curve here, so a much better agreement. And this shows the result of these different trajectories, these different calculations. What is plotted here are trajectories, so x versus t or t versus x. The yellow line here is, so to say, our simple man picture, where at the exit of the tunnel, which is well defined in a simple man picture, we launch our electron with 0 velocity at the position of the exit, and you get then this trajectory here, the yellow one. If we use, for example, the solution of our quantum calculation and now define a trajectory in terms of a Wigner trajectory, Same concept as you have heard. So we define a trajectory by just taking the derivative of the phase of our quantum solution with respect to the energy. Then we get this dashed curve here. In principle, we can extend this dashed curve to long distances, but we decided now that we want to match this dashed quantum solution with a classical solution or the classical propagation right at the classical exit point, and then propagate the particle with the initial parameters that we get from our quantum calculation. And if we do this, then we can extract the tunneling time, if you want, the time that we should plug in as a starting parameter for our classical trajectories as a function of the intensity, and the initial momentum, which we should put into our equation for the classical trajectory at the classical exit point of the tunnel. And if you do all this, and this was really amazing, this was kind of a real aha effect for me, we get a very, very good agreement, this experiment, so almost a perfect agreement. So if we include the values for the tunneling time, if you want, and the initial momentum into a classical propagation, a classical model, then we get perfect agreement with experiment. As I said, this was a kind of a surprising for me, but I leave it to you now to interpret these times as being a tunneling time or not, but this is a very well-defined concept, and it describes experiment very well. Let me come to my second subject, and this is rapid now. It's a rapid experiment, and during the last 2 years, we set up a high harmonic beamline in our lab. Here's a sketch of this beamline. So the laser is coming in, high harmonic source, and a reaction microscope. So we drive this thing with a fiber laser, 1,000 nanometers, up to 150 kilohertz. Power is going up to 150 watt. We drive our high harmonic source. It was a little bit tricky to get it running. Here's a more detailed view of our gas nozzle. Actually, these are 10 gas nozzles in a row. And you see the plasma that we ignite with about 150 watt here and produce harmonics. And these harmonics we send into our reaction microscope and do experiments, now kind of rapid type experiments. So this is a sketch of the XUV photons that we get. And if we do an experiment just with an atom, let's say argon in this case, then this is the photoelectrons that we get just using the harmonics. And you know that we now, if we also superimpose the IR field, then we get the so-called sidebands here. And we produce sidebands that now are sensitive to the time delay between the XUV pulses and the IR pulses. And here is a streaking trace of those electrons here as a function of the delay. You see the period is 1.7 femtoseconds, 1,000 nanometer laser. And again, now we can look for time shifts by looking at these phases here. Same concept holds. The phase shift is determined by the Wigner time and Coulomb-Coulomb coupling time. Okay, now let's do this with H2. A little bit more complicated, and I want to show you an experiment which is actually very similar to a recent experiment by the Zurich group, by Laura Cattaneo, published 2 years ago. They also measured rapid traces for H2. I will come back to this in a few minutes. So these are the data that we get for H2. So we produce a lot of singly charged molecular ions and fragments, H+. And if we look now to the electron spectra, this is already the superposition of XUV plus IR. So there should be a lot of sidebands. This is the electron spectrum here in the lower part. And you see everything is very much broadened. So it's hard to resolve even the sidebands. In some cases here you don't even see them. So it's very fuzzy. There's a good reason for this, because we ionize our H2 and end up in an H2 plus in the ground state, in the electronic ground state, but with a lot of vibrational excitation. This vibrational excitation can lead to a broadening in the order of 2 eV. That's just the distance between the harmonics here. So this broadening smears out everything. So what to do? There's a much easier concept. Let's look for another channel, for a more well-defined channel from the kinematic side. So we look for ionization plus dissociation. So we go from the ground state of H2 to a dissociating state here. And what is most likely happens that we go to the doubly excited state, a dissociating state, and then the total energy, the sum energy of the emitted electron and the kinetic energy of the ions is fixed. It's given by the XUV energy. So if you plot this energy partitioning here, you see sharp lines, and these are just the harmonics. Here we use XUV only. And the main channel in this spectrum here is coming from doubly excited Q states, where we excite 2 electrons at once. This state decays via autoionization. So an electron is emitted and the ions get some kinetic energy, and this is what is plotted here. Okay, so far so good. So now let's have a little bit closer look here and look to lower kinetic energies, because there the same concept works. You can also just ionize to the ground state of the molecular ion, and still get dissociation. Then you get lower kinetic energies of ions and well-resolved electron energies. But this is still without IR. Now let's switch on the IR for doing rapid or streaking. Then we see an additional lines here. These are the sideband lines. And you see a blob here at about 0.6 eV kinetic energy for the ions. And if you go, for example, on one of those sidebands here up, you see at some point, this, what was before a sideband, is now getting more prominent compared to the harmonics. So what's happening here is that that one electron is emitted by the XUV, and the remaining electron in the H2 plus is excited to the ungerade state. Then we get dissociation, and these are these sharp blobs here. Okay, let's go further, and now let's look to the phases here, and let's look, for example, for a selected kinetic energy window. We choose this part here, where we know that we have a contribution coming from these doubly excited Q states and direct ionization. And we also know that if we choose, for example, the ions preferentially emitted along the laser polarization, then we preferably have events coming from the doubly excited states. If we look perpendicular to the laser polarization, then the direct dissociation is a little bit more dominant. So we select a kinetic energy window for the ions here, and then look for the sidebands. And we look for the phases tau A here. And a closer analysis now shows us that these phases tau A, or shifts, are already converted, these shifts here, in time. So we see for parallel orientation, there is some jump going on here, some jump, a kind of characteristic structure where the perpendicular phases are more or less straight, smooth. And what is this? So this is appeared not just in one experiment, and actually what I'm showing here are data for D2, not H2, but D2. The reason I will explain in a second. So what happens here is exactly at these 29 eV or 30 eV here, we reach these Q states. So we excite the doubly excited states, the system rolls down here, and after some time, an electron is emitted via Auger ionization. So the question would be, has this time delay here between excitation and decay, is this somehow reflected in this yellow curve here? So what we did, we calculated just a classical propagation of the nuclear wave packet here along the Q states, and looked what kind of kinetic energy we get, kinetic energy for the ions as a function of the lifetime of these doubly excited states. And then you see for the kinetic energy window that we took between 0.1 and 0.4 eV, or let's take 0.2, a time of about 0.5 femtoseconds, 500 attoseconds for D2. If we do the same experiment for H2, this time is smaller. It's on the order of square root of 2 smaller, roughly. Sorry. So the interpretation now is that this jump here in the phase might be related to the lifetime of the doubly excited states here that we select with our kinetic energy release window. And now the problem is, in order to get a kind of an oscillation of the sidebands, we have to define somehow the interfering rapid pathways. This is not that easy here. With a single electron that is emitted in a single ionization, it's definitely easier, because you could imagine that we excite this doubly excited state via these two different paths here, coming directly from below or going first up and then re-emit an IR photon. But then the question would be, why do we then see a shift in time or in the phase? Or there are other possibilities that these IR photons interact during the decay, during the auto-ionization of the electron. In the moment, we simply don't know. And let me also compare this with the data from the Zurich group. They did very similar data for a much, much larger kinetic energy release range. So we should roughly compare the blue curve here with our yellow curve. You see that qualitatively there is agreement. Quantitatively, there is a difference, a big difference, because we measure much, much larger times here, about 0.5 femtoseconds, and they are in the range of 100 attoseconds. Interestingly, in their paper, they also had a theory calculation from Fernando Martin, and they even predicted also the similar shape, but the values are even lower by a further factor of 10. So you see, it's kind of a little bit tricky to interpret this data here. So we see sideband oscillations also in H2. The straightforward interpretation is getting much more difficult. It's not like in the single ionization of an atom. We expect, or we think, that these sideband phases are sensitive to the lifetimes, for example, for the doubly excited states. But eventually we need a theory to really get a quantitative understanding. Okay, I think I'm already a little bit over time, and with this I want to stop here. But I don't want to stop it without mentioning all the people that did the work. So in particular, the crew on the experiment. So this is Nicolas Camus from for the tunneling experiment, Farshad, M, Divya, and Anne for the high harmonics experiment, and we had help also for the tunneling case from theory from our institute here in Heidelberg. And with this, I want to thank you for your attention, and I will be happy to answer some of your questions. Thank you.
So thank you very much for your nice talk. Are there questions, comments? Just a remark, if your questions from the previous talk have not been answered, we would appreciate if you could post them on our Slack channel. They are sometimes arriving with a delay. So is there any question related to Robert's talk? I don't see any so far, but I have one, and this is related because you showed this picture from the theory developed by the Keitel group, and you showed that if you calculate a Wigner trajectory, works pretty well with regard to the experiments. Now, my question is, did they have to go to the complex plane? Did they not? Did they use a Wigner quasi-probability distribution? How did they compute that? Because we know that to calculate these things can be really hard, and sometimes you have to make approximations which can compromise your theory.
This is now a little bit hard for me to answer in detail as far as I understood it. So they solve the Schrödinger equation, the time independent Schrödinger equation for a static field, the binding potential plus the external laser field. This is a complex wave function, I'm sure. And from this wave function, they extract a Wigner trajectory, which they at least can provide, or also for motion under the tunnel, if you want, in quotation marks. But how they do it in detail, I simply cannot answer. So what is considered in the calculation, what is taken care of is the kind of multi-electron effects are included such that they use kind of a Hartley-Fock potential. What is also included is polarization of after the electron has been emitted of the remaining ion. So there are a few kind of tricks included in the calculation, but details I'm over-asked now.
Yeah, okay, fair enough. Thank you. Sergey, would you like to ask something? I can see you.
No, I just logged in, sorry.
No worries. Would you like to ask something? Okay, we have one in our Q&A, and this is from Jean Cheng. Can you fit the difference between argon and krypton in Attoscience clock measurement by only considering the initial longitudinal momentum without tunneling?
No. You get this. What fit means one gets an agreement with it is as good as it is now, with including the longitudinal momentum, the tunneling time. No, the agreement gets worse. This is not a huge effect, but it gets worse. So the best condition you get if you include the initial longitudinal momentum plus the tunneling time delay, if you want.
Are there any further questions? I cannot see any. They sometimes, there's one. Takes a time delay also for the questions, you know. So from Jens Bigard, I assume if two species rabbit use low gas pressures, would it be interesting, crazy to try a high pressure so that the ionic species influence each other differently? See old paper from Andreas Becker.
It is a low gas pressure. Yeah, I think I assume Jens is talking about the tunneling experiment with the krypton and argon. So this is definitely a kind of very dilute target. So individual atoms. I have no idea what happens if you use really a high pressure target. But because the trick here is also to kind of sign the emitted electron to its respective ion. So we need kind of do kind of coincidence measurement to label the electrons. If this would be possible with high density, I don't know. But maybe I simply misunderstood the question now.
Okay, can you clarify? Jens, can you type another one? If not, we should keep on moving. Please don't forget, if you would like to ask further questions, to type your questions on our Slack channel. We have one channel for each sections. And let's thank Robert again for his talk. So thank you so much.